Okay, so let's start. So here is what we want to prove. So we are going to finish the proof of specialization theorem, and here is what remains to be proven. To prove. So we have a discrete valuation domain A. Discrete valuation ring. And we have a scheme X over spec A. Here we have the generic fiber. And we have the special fiber, X0. And we assume that the special fiber is geometrically connected. And the main assumption is that this morphism is smooth. So then, so the assertion is the following. Let yk over xk be a Galois cover. With Galois group yk over xk equal to G. And we assume that the order of G is relatively prime to a characteristic of the residue field. Okay? Then the assertion is that there exists a finite separable extension. Finite separable. Okay, so here I have the ring of integers A, and here this is a finite separable extension, and I will denote by B the integral closure. So there exists such finite separable extension such that the cover x, y, L over xL, which is obtained from this one by the best change, extends to finite et al cover of xb, where xb is also obtained by the best change from x. Okay, so that's the picture. So notice that I do not assume here for this part of the argument this morphism need not be proper, and I do not assume that my A is complete. These two assumptions are needed for the other part of specialization theorem, namely to conclude that pi 1 of x0 is equal to pi 1 of x. Here, for this assertion, the morphism has to be proper, but need not be smooth. So there are two sort of independent steps in the proof of the specialization theorem. Okay? So let's prove this. First of all, so without loss of generality, I may assume that this cover is connected, right? Otherwise, I will apply this to every connected components. And moreover, I may assume that yk bar is connected. Well, if it's not connected, well, all the sort of connected components of this guy are defined over some finite separable extension of k. And so by replacing k by this finite separable extension, a by the integral closure, I may reduce the proof to this case when it's already connected. So I do the base change. I split this into this yk in the disjoint union of connected components and apply and so reduce the statement to the geometric connected case. Okay, so now this is the main step, step 2. Okay, so so let y be the normalization of x in the field of rational functions on yk. So what is this? So I have yl. This is yk. This is xk. And here I have, this is an open embedding into x. And assuming that these schemes are normal, which is definitely the case in our situation because x is smooth and this is a tull, there is a sort of canonical way to extend this morphism to a finite morphism from some y to x. Normalization. Okay? So in general, so this is a tull. This is finite. And this is normal. Okay? So if this morphism were a tull, we would be done. But in general, it's not. So, okay, so let's analyze what happens to this morphism. So, okay, let me see if I have enough room here. Да, даже решение было бы не нужно, абсолютно верно. So let me write this here. I need more room. So here I have x0, and this is the special fiber, and this is where I may have some troubles over x0. This morphism, this is going to be the special fiber. So everything is over spec A. This is over spec K. and this is the Cartesian square. So y0 is the fiber of this morphism over the closed point. So, okay. So let's take, let eta be the generic point of x0. So, and I need some names for this. Let's call this morphism F. So I have the local, so this is a generic point of the special fiber. So I have the local ring of x. Yeah, so I think I should. So here I have eta. And I will draw a larger picture. So again, here I have y, x, and here I have spectrum of the local ring of x at point eta. So eta is the generic point of x0. So it's a point of codimension 1 in x. Its closure is the whole x0 by definition. So I have this map. Okay, so now let's look at the Cartesian product. Let's take the fiber over this. So spec O x eta times y over x. So y is normalization of x in some finite separable extension of field of rational functions on x. So, and it follows that this guy is well, this is a finite morphism, so this is also a finite morphism. This is an affine scheme, and I can write it as well, it's spectrum of localization of y at f inverse of eta. Well, so one way of thinking about this scheme is that so you have Ox eta. Its fraction field is f functions on on x k, and here I have finite separable extension. This is yk. And what I have here is the normalization. This is y f inverse of eta. So this is normal and finite. Therefore, this is also normal. And therefore, this is nothing else but normalization, the integral closure of this discrete valuation ring in this finite field extension. So we are in the setup of ramification theory. So we have a discrete valuation ring, and we have a finite separable extension of the field of rational functions, and we take the integral closure. We want to analyze this ramification of these extensions of this DVR. This need not be DVR, but it has finitely many. It's a Dedekind domain with finitely many maximal ideals. Okay, so good. Let's see whether I can. So let M1 Mn be maximal ideals. Ideals of this normalization. So the notation that I'm using suggests that this is also kind of localization. F inverse of eta is a finite collection of points. So if you want to think geometrically, so this is my x, this is xk. The generic fiber is assumed to be connected, but the special fiber, x0, need not be connected. It may have several irreducible or even connected components. And this F inverse of eta is the set of all generic points of these connected components. So, if you have any scheme X and any set of points in X, you can consider kind of this notation stands for functions, rational functions that are regular on some open neighborhood of this collection of points. So I look at functions here which are regular, at least in a neighborhood on an open, dense open subset of y0. Good. So now this was a yk was a Galois cover. So the Galois group G acts here. And therefore, because the normalization is, it's a functorial construction, it's just the integral closure, G still acts here. All right? The action of G on the generic fiber extends to an action on Y. And because this guy is obtained by the best change, the Galois group, this is a Galois cover. This is a Galois extension. So G acts here. And it also acts here. It acts on everything. And we already observed that in this situation, this G permutes these maximal ideals. G acts transitively on this set of maximal ideals. It permutes components, irreducible components of the special fiber of y0. Now, I have OX eta. This is a discrete valuation ring. And I have here a maximal ideal. And, I claim that this maximal ideal is generated by the uniformizer A. So let me add to this notation. So I have A. This is a discrete valuation ring. And I have a maximal ideal. It's a principal ideal. It's generated by some uniformizer I. So, and I claim that this M, this maximal ideal here, is also generated by this same element pi. Why is that? So first of all, this pi, it's equal identically 0 on x0, right? So it means that it's equal to 0 on y0, so it's this pi sits in the maximal ideal. But I claim that this maximal ideal is actually equal to pi, is generated by pi. Well, every ideal in discrete evaluation ring is a power of maximal ideal. So that's a priori, this M is generated, well, it's also a principal ideal. It's generated by some uniformizer pi prime. But if, so I could write that this is equal to pi prime, but then pi must be equal to pi prime to some integer ramification, maybe. I don't want to, let me call it E, capital E, times a unit. Right? I can write any element of discrete evaluation ring in this form. And you see that if E is greater than 1, then the quotient of this ring, modulo pi, would have nilpotent elements. Right? Namely, so you look at the x eta modulo pi. So if pi is not maximal, then so that means that pi prime is not 0 here, it would be a nilpotent element. But what is written here is just the local ring of the generic point of x0. x0 is smooth because the morphism is assumed to be smooth. So in particular, x0 has no nilpotence. So x0 is cut by equation pi equal to 0. So the ring of the fact that x0 is reduced means that, well, that pi is equal to pi prime up to a unit. Okay? So this is explanation for this equality. Okay, that's what we have. Good. Yeah, I think I want to erase this. Okay, so now we have this Dedekind domain. It has this finite number of maximal ideals, and it's an extension of a discrete evaluation ring with maximal ideal M. So I can write that M, which is generated by pi, equal to product of maximal ideals, powers of maximal ideals here. And the exponents, well, they are all equal. Again, because this is a Galois extension. Because the Galois group acts transitively on the set of maximal ideals. And this is what we call the ramification indices. Good. So, so what? So if I write Mi, this is a maximal ideal here, and we already observed that all these ideals are principal. So I denote by pi I uniform generator. Then well, so let me introduce one more piece of notation. So f inverse of eta, well, this corresponds to maximal ideas here. These are generic points of the special fiber of y, or y0. And I will denote this set eta 1, eta n. So I have y f inverse of eta. This is not a local ring. It's a semi-local. It has finitely many maximal ideals. And I can look at its localization at points here. So y eta I. This is already a discrete valuation ring. And it also has maximal ideals there. Well, that's maximal ideal. It's generated by the same pi. And here, well, I have two elements. I have pi and this pi I. And because of this formula, pi is equal to u times pi I to this ramification index, where u is an invertible element in this local ring. Good. So what else do we have? So we also have, we know something about this ramification indices. We know that E multiplied by the base field, the residue field extension, F, degree of the residue field extension, times the degree, the number of these points, is equal to the degree of this field extension, which is a Goulart extension with Goulart group G. So it's equal to the order of G. So, and F, I recall, it's equal to the degree of the residue field extension. So it's k eta I over k eta. So this guy is relatively prime to characteristic. So it follows that E is also relatively prime to characteristic. And F is also relatively prime to characteristic. And this is all equal 1. And this implies, in particular, that well, this degree is relatively prime to characteristic, so it means that it's separable, right? So if characteristic is P, well, any extension of degree coprime to P is separable. Is separable. And E is also. That is not divisible by P. Now I can construct L. So our goal is to produce the cell and then an extension of this base change. So set L be k of pi. Pi is a uniformizer in A. I add eth root of pi. So this is also a separable extension because E is coprime to P. And in particular, coprime to characteristic of capital K if it's not 0. Okay, so we Well, I told you what L is going to be. Now I will tell you what YB is going to be. So here I have my B. And I set YB to be the normalization of X in field of rational functions on YL. So I take YK and I do the best change. This, by our assumption from step 1, is a field of rational functions on YK tensor over K with L. So, and our goal will be to show that YB is a tal, finite a tal over XB. Да, конечно, можно. Вот. Окей.
Была на самом деле в основном вот за характеристику, чтобы как бы, чтобы сразу же, Е было взаимно просто с характеристикой.
Да, ну нам надо два условия, что Е взаимно просто и что вот это расширение сепарабельно. Это тоже важно. Okay, so now let's consider the following picture. So we have, so I will draw a big diagram here. So I have X, I have Y, I have YB. This is the base change. I have spec OX eta sitting here. I have spec OX F inverse of eta sitting here. And now I will consider the fiber product of these two schemes. So let me see how I want to. I will write it as spec or X. Sorry, this is Y. This is YB at F inverse B of eta. So these are all extensions of Dedekind domains, right? So I take, I have corresponding, so I have field of rational functions on X. I have larger field of rational functions on Y, and I have a field of rational functions on YB. And here I have my OX eta. And so I take the normalization in this finite separable extension. So this will be O YB F inverse of eta. Okay? Good. Now, there is another part of this, of the diagram. So let's study this morphism here. So what can we say about this? So, well, this is a Dedekind domain. It's a semi-local ring. It has finitely many maximal ideals. Let's cover it by localization of this maximal ideal. So let's look at open subsets, or Y eta I. And let's take the fiber of this morphism over this open subset. And I claim that we can describe it very explicitly, and that will be the key point. So let's look at this formula here. So our field extension, where we take normalization, well, it has pi I in it, and it also has eth root of pi. We just added it, right? This is here. So in particular, it has eth root of u. And I claim that this is nothing else but spec or y eta I, and then I add to it 1 over e of u. So let's see why this is the case. So I'm saying that normalization of this guy in here is the spectrum of this ring. Well, first of all, if you look at the fraction field, it has this root of u, and it also has pi I, so it has eth root of pi. And therefore, the fraction field of this guy is precisely what we have here, because this field is obtained from this by adjoining eth root of pi. Secondly, because u is invertible, u is a unit here, and e is coprime to characteristic, this morphism is a tal, right? I extract eth root of invertible function on a manifold, on a variety. So this morphism is a tal. Finite a tal. Вот я сейчас объясняю, что мне надо проверить. И вот мне надо проверить два условия. Что, во-первых, эта штука целозамкнута, а во-вторых, что поличастных то, которое нужно. Но то, что поличастных, которое нужно, это понятно, потому что... А мне надо проверить, что она целозамкнута. А для этого я сейчас хочу объяснить, что вот это отображение тально. А поскольку это целозамкнуто, вот это тоже будет целозамкнуто. Если у меня есть этальное отображение, база нормальна, то тотальное пространство тоже нормально. Давай я сейчас это не буду доказывать. Давай я, давай я этот факт запишу. Может быть, если останется время, я объясню. Просто это будет немножко такое отступление. Ну, оно такое, тут надо что-то использовать про нормализацию, про нормальные схемы. Оно очень простое, если что-то знать. Значит, факт с критерий Серра.
Что на формальных, ну, что при выполнении оно становится...
Например, или критерий Серра нормальности. Ага. Значит, если вот это этальное, then Z1 is normal implies that Z2 is normal. Yes, so maybe technically that's not the easiest, the shortest argument, but conceptually probably what Volodya suggested is the most understandable. So an etalomorphism induces isomorphism on completed local rings, and that's enough. А нормализация, она сохраняется как бы при выполнении. В общем, чтобы доказать, что локальное кольцо нормально, достаточно доказать, что его выполнение нормально. В эту сторону. Вот. Но технически, значит, проще иначе. Короче. Okay, so again, informally, a morphism is etal if it's kind of very locally an isomorphism, and normality is a very local statement property. So good. Now, so this is etal, finite etal, therefore it's normal, and therefore that's normalization. So I have so in this diagram, well, all these squares are Cartesian. That's normalization, that's normalization. Okay. So we have a very explicit description, and now so let's consider the following diagram. Again, so we have OR X eta. We have various extensions of Dedekind domains. So we have OR Y eta I. This is ramified with ramification degree E. We have this guy, or Y eta I adjoint 1 over E. And so that means that here I have this is etal. Right? So in particular, all the ramification degrees are 1. Right? This is a Dedekind domain, this is a Dedekind domain. So if I take well, any maximal ideal here is generated by the uniformizer here. That's what it means that it's etal. And finally, I have or XB eta. So this field L is totally, well, it's kind of ramified extension. So this little k, the residue field, does not get extended. The residue field of L is the same as the residue field of k. So that means that the special fiber of this scheme is also x0, so it has the same generic point. That's why I use this notation. So, OK. So I have this diagram. So here, ramification is E. Here, ramification is also E. Well, in fact, this extension is very simple. It's just obtained from this local ring by adjoining eth root of pi. Pi is a uniformizer in A. So by the very definition, its ramification is E. So, and this is unramified. So the ramification of this guy over this, all the ramification indices here are equal to E. And that means that here it's already E. So it means that this is unramified. And the base field, the residue field extension is separable. So this is a fine. OK? And then we are done. Sorry, we are done with step 2. So, OK. So step, I will summarize what we did. So in the beginning of this step 3, I will summarize what we have. So we have, we choose some L, and we have the normalization yb over xb. And so we know that this is finite. Yb is normal. We just checked, and this was the content of step 2, that this morphism is étal, this morphism is étal in codimension 1. So what does it mean that it's étal in codimension 1? Well, it means that if you pick any point of codimension 1 and take its local ring, spectrum of its local ring, and take the fiber product, the fiber over this local ring, right? So you, for example, here I can take spec or x b eta. Eta is the generic point of the special fiber. And take, so the content of this step 2 was precisely the following. We just proved that, so if I take this finite cover, finite morphism, and take the fiber product, yb times spec of ox b eta, then this is étal. Right? So how we check this, we prove that this is étal. So, and here I claim more that it's not only for this point of codimension 1, but for all points of codimension 1, the same property holds. Why is that? Because all other points of codimension 1 are in the generic fiber. I have one point of codimension 1 which is in the special fiber, and all other the generic fiber is the morphism on the generic fibers is étale by assumption. There is nothing to prove. So very good. And one additional property is that xb is regular. Well, because B is a Dedekind domain, and xb is smooth over Dedekind domain, and any scheme which is smooth over Dedekind domain is itself smooth, is regular. Or any scheme which is smooth over regular scheme is regular. Okay, so and now we are in a situation where we can apply our purity theory. So if you have a finite morphism from a normal scheme, which is a finite surjective morphism from a normal scheme to something regular, which is étale in codimension 1, then it's étale everywhere, right? So remember how we formulated this purity theorem. If you have any finite étale cover of a punctured surface, of a surface minus 1 point, extends to a finite étale cover over a surface. The fundamental group of a punctured surface is the same as the fundamental group of the surface. Surface is something of dimension 2, regular of dimension 2. And that's also true for in higher dimensions. So if you take some regular scheme and you remove something, closet subscheme of codimension greater than 1, it doesn't change the fundamental group. Explicitly, it means that any finite étale cover over a complement over this open piece extends to a finite étale cover. And if it extends, it must be the normalization, because a finite étale cover over a regular scheme, in particular normal, is also normal, so it must be the normalization. So by purity theorem, the morphism from YB to XB is étale. Okay? Good. This completes the proof. Now, I want to, so let's recall for the last time the statement of the specialization theorem what we have already proven. So it's very simple. You just take so K is C T, A is C Taylor series, and I will take a very stupid example. I will take xk, and my yk is going to be just xk tensored over k by c T1 over E. Right? So it's étale because this is a Gola extension of this field, right? Its Gola group is Z mod EZ. So what happens if you take the normalization? Well, so if you consider X here, and you take the normalization, which is Y, it's simply going to be Y X tensor with C adjoint 1 over, okay. That's going to be this. So this morphism is obtained by the base change from this finite morphism. And this is, of course, not null because its special fiber is not reduced, right? You take this and mod it out by DOT equals 0, you get something non-reduced. So we see that this normalization is not at all. But now what happens when you do this field extension? Well, in this case, the situation is simple. So when you replace K by this field, this extension gets split into disjoint union of XL. And then the normalization is going to be just a disjoint union of copies of X tensor with this ring, but you consider it as a scheme over itself. So it's a tunnel.
What if YK is geometrically connected, so less stupid? Could this ramification still happen?
Yes. So let's take, imagine that you have, let's look at the more interesting example. So let's take, let's pick an invertible function on OX. As we already observed, X need not be proper here, so it could be many invertible functions. And let's sort of simply extract, we can do the following. So I have an invertible function, and I can consider a morphism from xk to gm. This is the multiplicative group over k, which is given by the following formula: u times is it right, u times t. T is my element here, right? Does it make sense? And now I take the cover that takes z to the e. So I just extract a root of this. Then, well, so this will be my yk, the base change. So I just extract the root of this guy. And then you see that, well, this itself does not extend. This y over x will be ramified. But when I do the same base change, well, then, so when I add eth root of t, then the cover is obtained by extracting eth root of u. And this morphism is already a null. That was the trick.
So in a fine curve, y to the e equals utx, right?
Yeah.
So like
Yeah. Good. So, specialization theorem. So we have X over spec A smooth and proper, connected, geometrically connected fibers with proper A, say, complete DVR.
Чего нам нужна будет в конечном итоге эта теорема, чтобы фундаментальный класс определить дивизора?
Ну и сейчас, нет, ну чтобы вообще нужна, чтобы как-то понять, как устроены накрытия, например, кривой в характеристике P. Сейчас я приведу пример еще раз. So the residue field is algebraically closed, and then final assumption is that x0 is connected. And then we have the following morphisms from pi1 of xk bar to pi1 of xk. That's bifunctoriality. Then we have pi1 of x. That's again given by the inclusion. And here I have pi1 of x0. And because this morphism is proper, this is an isomorphism. And the specialization is the composition. And the statement was that it's surjective and isomorphism on coprime to characteristic of the residue field quotients. So that's what we proved. And I want to make a remark which is not a mathematical remark. It's, but maybe it still helps. So So here is a topological picture here, which is kind of trivial. Therefore, it's not, but still it explains some notations that we use here. So, so let's take, let D be a disk, complex disk. So it's set of points in C with absolute value of Z less than 1. And suppose I have a family which is, say, C infinity manifold, smooth and proper. What it means is that this is a smooth manifold, and this map is surjective on tangent spaces. Properness means, well, usual preimage of compact is compact.
But actually, he knows that x is just t times y.
Yeah, yes. So non-canonically, right. So here I have the puncture disk. Okay. Puncture disk. And here I have x d star. That's the base change. Here I have x0. That's sort of over 0, the fiber. Now, so I want to look at kind of analog of this specialization map. So what is the fundamental group of this guy? I think of this as a substitute for this in terms of the fundamental group of x0. Произведение. Потому что, как тут было замечено, x не канонически изоморфно просто x0 умножить на диск. Потому что любое такое гладкое собственное отображение, оно топологически is topologically fiber bundle. And fiber bundle over something contractible is trivial. So this is simply the product of a fiber times d star. But now, if you take the universal cover of the puncture disk, which is analog of k bar, so what is universal cover of the puncture disk? I can think of this as a set of complex numbers, tau, with imaginary part of tau greater than 0. That's upper half plane. And the map takes tau to exponential of 2 pi I tau. All right? And if you form this fiber product, then, well, you still have map from pi 1 of x. So you take this x over puncture disk, you lift it to the universal cover. Well, by functoriality, you have this projection. Then you can map it to pi 1 of x d, well, x. And here I have pi 1 of x0. So, and in this diagram, this is an isomorphism, so you get this map. And this is, well, an isomorphism under weaker assumptions.
Wait, I think you have the imaginary part of tau to be greater than 1, because if you take like this, then it will cover c star, and you need d star.
OK, thank you. Thank you. Let me put some constant for safety. So specialization. And so this specialization map, this composition, is also an isomorphism. OK? So that's kind of trivial, but still it's at least notationally it's similar to what we have here. Now, a non-trivial example where the theorem, the specialization theorem, is really deep is the following. So let's take example. Let's take a curve over K, where, so K is algebraically closed field of characteristic of K is P and greater than 0. And this is smooth proper curve. Then there exists a smooth proper curve. So in order to apply the theorem, well, I need a discrete foliation ring, right? So I claim that there exists a smooth proper curve X over the spectrum. So I'm interested in computing the fundamental group of X0. That's my goal. And in order to achieve this, I will leave this curve in characteristic 0. Well, first I need to take this K and leave this in characteristic 0. So I take the Witt vectors of that. Such that X tensored with K over Witt vectors as my X0. So I claim that any curve in characteristic P can be lifted to a curve over the Witt vectors. So, well, what does it mean? A curve. So what is a smooth proper curve? It means that it's a smooth proper morphism. Essentially nothing else. So it's all other conditions are automatic. So in particular, the generic fiber is also going to be a smooth proper curve. So, so why that? That requires an argument. It's not true in higher dimension in general. But the argument is, well, it uses the algebraization theorem of Grothendieck that we already used once. So the idea is the following. You take X0. X0 sits over, it's a curve over K. Now you take spec of Witt vectors. Да нет, основная борьба сейчас будет за алгебраичность. Okay, so I take this infinite degree level order 1, order 2 thickening, nilpotent thickening with square 0 ideal, right? So this K is the quotient of the Witt vectors modulo P, because P is because K is perfect, it's algebraically closed. So, and well, the idea is to kind of think of Witt vectors as sort of limit of truncated Witt vectors. And so on. So, and then we can try to construct this X step by step by first constructing a smooth proper morphism X1 over this guy, whose special fiber is X0. Well, so that's, in general, even this in higher dimension is not possible. You cannot, there are examples of scheme over FP bar that cannot be lifted modulo P squared. But nevertheless, there is a homological abstraction to the existence of a lifting. So, well, first of all, if you have a smooth scheme over X0, smooth scheme over spec K, then locally, locally on X0, a lifting exists. Oh, because any smooth scheme, the risky locally, can be can be embedded into a affine space and given in a affine space by system of equations satisfying the Jacobian criterion of smoothness. And then you simply leave the coefficients of these equations, modulo p squared, arbitrary. It will still satisfy the Jacobian criterion of smoothness, and therefore we are done. So locally on x0, such x1 exists. Moreover, you can show that any two liftings locally are isomorphic. Any two smooth liftings locally are isomorphic. That follows from infinitesimal criteria of smoothness. So any two smooth liftings are étale over their affine space. So you can think of x1 and x1 prime as covers of the affine space, open subset of affine space. And now any isomorphism over a closed fiber, over a affine space over this guy, can be extended to an isomorphism over the entire affine space because the infinitesimal property of étaleness. So you have the following situation. Liftings exist locally, and locally they are isomorphic. But this isomorphism is not canonical, right? So there are automorphisms of this scheme which are equal to identity modulo p. What is the group of automorphism of x1 that is equal to identity modulo x0, modulo p? So consider automorphisms here, which are identity here. What is this group? It can be described easily in terms of vector fields. Think of just a ring over z mod p squared z, commutative ring. And you're looking at automorphism of this ring, which is modulo p identity. I claim that any such automorphism has the form identity plus p times derivation. So that means that automorphism of x1, which are identity here, is the tangent vector fields. So in this situation, it's formal to see that the abstractions to the existence of a lifting lives in H2 of x0 with coefficients in the tangent sheaf. How you do this? You simply pick a cover x0 by affine open subsets, pick local liftings. Pick local isomorphism between these liftings on the intersection. But then it doesn't satisfy the cocycle condition that you need to glue it. And this cocycle, because this isomorphism will not be on the intersections, will not be compatible on the triple intersections. So on the triple intersections, you get a Čech 2 cocycle with values in vector fields. That's how you construct an element here, which is an abstraction to the existence of a lift. But fortunately, when x is a curve, this group is 0, because it's one-dimensional, and this is H2. So this is 0. Therefore, x1 exists. But then you can construct x2, and using the same technique. And it turns out that the abstraction, if you apply the same kind of argument, you look at automorphism of x2, which are now equal to identity modulo x1, and they all have the form identity plus p squared times the derivation. It's still the abstraction lives in the same group, the same x0. It could be a different abstraction, but it belongs to the same group. So this way you can construct a family. Well, you can sort of construct thickenings over liftings modulo p squared, p cubed, and so on and so forth. And then you want to say that that defines for you the smooth scheme over spec W of k such that its reduction modulo p is 0. But unfortunately, here is a gap in this argument. Given a scheme over this is not the same as given a collection of schemes over these reductions. Even if you think about affine schemes, you don't want to say that given a ring over ZP is the same thing as given the family, compatible family of its reduction modulo P to the nth power, right? So if you assume that your ring is complete, then yes. But functions on affine varieties over ZP are not complete. Like take A1. So it's not at all automatic, and it's not true in general that even if all these kind of abstraction classes, if you have a scheme and characteristic P, and even if you know that these liftings do exist, you can construct a compatible chain. If you can conclude for some reason, for example, that this group is 0, it's not true in general that an arbitrary kind of chain of infinitesimal liftings gives you a scheme over the Witt vectors. For example, it may happen for abelian varieties. So you can start with an abelian variety. It's not that difficult to show that any abelian variety modulo p squared, modulo p admits a lifting modulo p squared, and then modulo p cubed, and so on. So this group is not 0, but still there is a kind of abelian varieties have too many symmetries. You can conclude that the abstraction class here is 0. But if you kind of carelessly choose arbitrary lifts of your abelian varieties, modulo p squared, p cubed, and so on and so forth, then it doesn't give you an abelian variety over ZP, over periodic integers. It's not algebraizable. It gives you something called rigid analytic torus, right? So it's, there is a, like in complex picture, there is a complex tori which are not algebraizable. So over ZP, there is something like this. So in order to construct X, you, so the idea, which is, well, the idea of Grothendieck is that it works well, it works okay, if you are given not only lifting of X0, but if you're also given a lift of an ample line bundle on X0. So what you need is to lift a pair consisting of X0 and an ample line bundle. Вообще, всегда. So the idea then is very simple. So if you can construct, so if you can kind of leave the pair X and ample line bundle, then so what you do, you just use this ample line bundle to embed each xn into projective space. So then xn is cut by some polynomial equations in it's a quotient of the ring of homogeneous polynomials modulo homogeneous ideal, and sort of so the homogeneous coordinate ring on X is going to be just the limit. It's going to be the limit of homogeneous coordinate rings of Xn. So the key point here is that the vector space of homogeneous polynomials of given degree is finite dimensional, or finitely generated over Z mod P to the NZ. And therefore, its limit is automatically periodically complete. Well, therefore, if your variety is over ZP, it's automatically periodically complete. Well, it requires a proof, and I'm not kind of explaining maybe I tried to explain the intuition, possibly failed, but this is a non-trivial theorem, but very general, that if you can lift X0 together with a line bundle, ample line bundle, then you're in a good shape.
Can we just, make it arbitrary sections that K to X naught and so on, and we just be ample because on the curve the point is ample?
Yes. So here it's not a big deal. So there are no abstractions, in fact, to lift in ample any line bundle, because the abstraction still lives in H2. So okay, so I need to stop here. So I wanted to formulate what the answer, but my time is over. So what the kind of summary of this discussion, I wanted to explain why a curve in characteristic P can be lifted to a curve in characteristic 0. This is an important fact, and I will use it tomorrow. Surprisingly, it's also true for abelian varieties, and it's a difficult theorem, whose proof consists of two steps. You first prove the existence of infinitesimal liftings. This requires vanishing some abstraction classes, and then you work really hard to make this to lift ample line bundles, and then in order to do this, you have to possibly modify your infinitesimal liftings. Otherwise, it will not be algebraizable. And I think this is done by delineation using a very, very tricky global argument with model space of abelian varieties.